in detail. We just want to get an idea of chemical equilibrium and just have some rough familiarity with it. Let's talk about the conditions of equilibrium. This previews some of the slides here. Reversibility of chemical equilibrium, collision theory of chemical reactions, molecular physics. So when we've done chemical reactions so far, we look at it for the driving force. If there's a driving force, then yes, reaction. If there's no driving force, then it's going the opposite way. We say no reaction. If there's yes, then we just do our standard stoichiometry. We can make our predictions based on the stoichiometry. But what about for partial reactions? And typically when we're doing this, if there's a driving force, we say that the products here are more stable than the reactants. And so this would be in terms of energy here. And so the balance is, if there's a driving force, the products are more stable. We want to go downhill to lower the energy of we call the system. If there's no reaction, then just the opposite scenario happens. If we plot energy, this is just some energy axis. On the y, we'll see that the reactants are down here, and then the products are way up here. So this is another possible scenario. And so, therefore, there's a big uphill battle to get the products in this case. Here. But there are some reactions where we're going to have partial reaction, or in other words, these are what we call reversible reactions. And that is, we have these partial reactions, and the extent of the partial reaction depends on different factors. But here, on partial reactions, we could have ones that are slightly product favored, maybe. That is, we'll still have a driving force, so we can go from reactant to product. Here, but the driving force is not huge. That is, there's not a huge difference in the stability of the reactant and the products. Or it might even be unfavored, but it's not hugely unfavored. That is, again, when we look, here we expect to see a driving force, but it's not a big driving force. And so here, driving force, but not so significant, but not big. Here, there's no driving force, but the barrier is not so big. But the barrier, that is, not big. And so in both these instances, we have a driving force, but it's not so huge. And that is, the product and the reactants are kind of comparable. Or we have no driving force, but that no driving force is not that big of an uphill battle that some reaction can occur. Or in this case, where the reactants and the products are the same energy, then it makes no difference. The reactants and products are the same energy. Then both are favored. And so here, reactants are slightly favored. Here, products are slightly favored. So we'll say products slightly favored, but not enough to drive this to 100%. Here, reactants are slightly favored. Here, both are favored. You know, both are equally. In all these scenarios, what we're going to get is this partial reaction. When we have partial reactions, then we have to do a special kind of stoichiometry that's required. For partial reactions, standard stoichiometry does not work. So let's talk a little bit about this. We call these equilibria systems. There's going to be some kind of equilibrium that's going to result. And so we call this product slightly favored. That's the equilibrium. The equilibrium favors the products. Over here, you know, this is kind of an equilibrium situation, but in this case, you know, the products are heavily favored. And so it's pretty much 100% reaction here. Okay, in this equilibrium here, the reactants are slightly favored. And in this equilibrium, both sides are favored, so you expect an equal mix of everything. And so this is what this slide's talking about. This slide's talking about this equilibrium that exists between reactant and product, you know. And, you know, whenever we're talking about an equilibrium, it's always a dynamic equilibrium. We've talked about equilibrium situations before. What was the first equilibrium we talked about? First equilibrium was it vapor pressure, maybe? Do you remember the vapor pressure equilibrium? You know, once the air is saturated and it's 100% humid, can it be even more humid, like 110% humid? No. And so that's an equilibrium. We've reached this. Okay, so we wait and reach this state. Okay, once this reaction, we waited for this reaction to take place, and once we've waited, that's it. You know, in certain cases, we'll only get like 10% reaction occur, you know? Like maybe here. 10%, or over here, maybe 20% reaction occurs. Something like that. And we'll wait, and then that's it. There's no more that's going to occur. And so what it means to be in equilibrium, that means that, you know, it's not going to go to all products, like here. In our standard stoichiometry, we'll always predict we get complete reaction. Limiting reagents always consume completely, and we form the product, right? Over here, though, we'll have some kind of equilibrium. Now, the equilibrium means the reaction doesn't stop. This is what it means to be reversible. What happens in this equilibrium is that the forward reaction occurs and the reverse reaction occurs. We've seen an equilibrium reaction before, and that has to do with water. What was the equilibrium reaction that we saw for water? This equilibrium is what causes the pH water to be 7. Yeah. What was that equilibrium called? Yeah, there's an equilibrium constant called Kw for water. It was called water. Yeah, it's a water constant. It was 1.0 times 10 to the minus 14. Mm-hmm. The number that a lot of people memorize. has to do with this reaction here. This is a dynamic equilibrium. A dynamic equilibrium, we've seen equilibrium before, they're dynamic, and what happens is the forward reaction never stops. Forward reaction never stops because you can't stop water molecules from colliding with each other. They're just going to naturally collide with each other. The water molecules collide, but only a tiny, tiny fraction. Over here, this is this type of scenario where the reactants are heavily favored over the products. But since there's a tiny fraction that is capable of reaction, we're going to generate just minute quantities of hydronium hydroxide. No matter how long we wait, if we wait longer and longer, will this concentration grow? No, once it hits this point where we've reached this equilibrium, the concentration is here. But won't the concentration decrease, diminish also? That is, once we hit 10 to the minus 7 molar hydronium, shouldn't that go down as this reverse reaction takes place? Shouldn't the 10 to the minus 7 molar go up? In other words, shouldn't the pH increase and decrease the time? And the reality is it doesn't. The pH stays constant. That's because the two processes are continually happening. The collisions generating this, you can't stop those. That's the forward reaction. And hydronium loves hydroxide. This is strong acid, strong base. They're going to react, and there's a reverse reaction takes place. And so this is the dynamic part of the equilibrium. The dynamic part is that this reversible reaction. So both the forward reaction and the reverse reaction go. The only point is one side is heavily favored. Which side is heavily favored energetically? Well, heavily favored in terms of being stable. Which side is much more stable? Water. And so it's a case like this, the reactants are more stable. Depends on how big this barrier is declined. Right now, what did I say about how many water molecules have enough energy to go off this? About, if I had 1 billion water molecules, about how many are capable of reacting to form hydronium and hydroxide?
Was it like 3?
Close. Very close. I didn't say 3. Is that what you have in your notes?
No, that's what I thought.
That's what you thought is very, very close. So something in your subconscious is trying to tell you the number.
It was around 3 or something.
Yeah, it was around 3. But I gave you a specific number.
2.7.
Not 2.7.
No, isn't it 22.7?
No, not 22.7. Nobody wrote it down? I showed it in combination with the curve. The curve.
Oh, 4.
4.
Yeah, I got it. 4.
It was with that curve. What was that curve called? It wasn't in this chapter. It was in the previous chapter. It was in the vapor pressure chapter. Remember the vapor pressure?
Yeah.
What curve am I talking about?
It was like the curve that showed like the minimum energy for self-ionization.
Yeah.
Like that little cutoff.
The cutoff, right. Exactly. Can you visualize that curve I'm talking about in your head? And so I just modified this to talk about that autoionization. This energy barrier, the cutoff is way up here. It depends, the cutoff is. The energy is quite high, so the cutoff is way out here, so it's only a tiny, tiny fraction, 4 out of 1 billion. This is for vaporization of water. The cutoff for water vaporization is way lower. It doesn't cost as much energy to vaporize off the surface. But we can apply the same curve. This is the same curve as water, so it's the same curve. Just different cutoff energy. This is the cutoff energy for molecules have enough energy to evaporate, and the cutoff energy for autoionization is way up here. Okay. So again, even though you look at these arrows and they're even size, that doesn't mean that it's a 50-50 mix. You know, the even size comes from this. You know, the even size comes from you've reached a state of dynamic equilibrium where the forward and the reverse processes have balanced each other out. But one side is heavily favored. And in fact, in water ionization, the water is heavily favored, the hydronium hydroxide isn't. And so in that case, we're still going to write these like this, except, you know, one side's favored the other side. And so the one side's bigger than the other side, but you don't see it from just these arrows here. And so the equilibrium is a closed system, dynamic in nature. Closed system means, okay, closed system we use for a lot of things. Closed system means this, you know. What can happen in these equilibria is that you can start removing stuff. So we don't want to add things and we don't want to remove things because that can upset the equilibrium. You know, equilibrium. This is one way of thinking about equilibrium that I use, and this is the water bath or water tank analogy. And so closed system is you have a fixed amount of water. Let's say I have like 50 gallons of water and I have a tub that looks like this. 50 gallons. And I draw the double arrow like this because water is free to move from the right tank to the left tank and the left tank to the right tank. The right tank we're going to label as the reactants. The left tank, the right tank will label as the products. So looking at this water tank, which side is favored? Which side is favored? Well, most of the water is on the left tank. And so the same thing goes with atoms. You know, we have a fixed number of atoms. Most of the atoms are on the right side or the left side. Most of the atoms are on the left side. Okay? And so this is showing that the reactants are favored. That is, the reactants must be more stable in energy than the products. And so the reactants are favored here. But we have this situation where it's a dynamic equilibrium. Are the water levels changing? The water levels aren't changing. Oh, if the water levels aren't changing, that means there's no movement of water. Is there no movement of water? Are the water molecules frozen or are they free to move? No, the water molecules are free to move. And so the water molecules are moving back and forth, but there's no change in the level here because it's reached a state of equilibrium. So we might start off with all reactants, but eventually we'll reach a situation like this. This would be like this first scenario here. In the second scenario, it's just the product tank is a little bigger. You know, and the size of the tank just depends on, you know, how big or how small the driving force is or isn't. And so here, again, we're looking at reactant and product. When we have a 50-50 situation, then the tanks are equal in size. So we have 25 gallons and 25 gallons on both sides. Okay, so this is where we see the different scenarios. This is one way to visualize what's happening in these reactions. Now, what a closed system means is we have 50 gallons. What do you think would happen if I start sucking some water out of here? If I start sucking water out of here, let's say I got a hose and started removing water from this side, which way is the water going to shift?
Towards the product.
Yeah, it's going to shift towards the product. That's not a closed system because what I'm doing is I'm taking away product, which is going to force this to make more product. Or what happens if I add more water to this side? If I add more water to this side, I'm going to make more product. Or what if I take reactant out? If I start removing reactant, then it's going to go backwards and make more reactant. And so closed system means I don't remove or I don't add anything. That's what it means, right? But in chemistry, we often remove and add things. What I just explained to you is what we call Le Chatelier's principle. Le Chatelier's principle says that if I add or remove things, that's going to upset the equilibrium, right? The balance, that's all. And so this is what we call a dynamic equilibrium. The water is still free to move, the atoms are free to move, and you can't stop the collisions. The collisions are going to happen in both directions. Results in zero net change, zero macroscopic change. If we look at the particular level, things are always reacting. That's what they mean by here. Forward and reverse rate of change are equal in an equilibrium. That is, the forward and reverse, for every water that moves right, one water molecule moves left. So we have a state dynamic equilibrium. Let's see what's happening here. Solutions of calcium chloride left and sodium bicarbonate right. Sodium and chloride ions as spectators are not shown. So we have calcium and bicarbonate. A precipitate of calcium carbonate and some carbon dioxide gas is generated. So this is a mix of reactions here. It's a forward reaction. Okay, if we look at the reverse reaction is carbon dioxide, calcium carbonate. So let's see what's happening here. Calcium carbonate dissolves when the solution has been saturated with carbon dioxide. So the reaction can be reversed by bubbling CO2 into the calcium carbonate. And so they're bubbling CO2 here, which is going to dissolve the calcium carbonate. And so this on the forward and reverse reaction can happen. Some reactions aren't so simple to reverse. Some reactions are pretty much one way, and that's it. They're very difficult to reverse because of something called the mechanism of the reaction. Other reactions are easy to reverse, but still one side's favored over the other, usually in these types of things. And so it depends on the collisions. Some reactions are hard, like, for example, batteries. Shouldn't you be able to recharge all batteries? Aren't all chemical reactions reversible? No, the chemical reaction that happens in primary, what we call primary batteries, is hard to reverse. You could try to reverse it by putting it into recharger, but it doesn't. It's just going to overheat and potentially explode from the pressure that's generated in there. And so what they did was they designed rechargeable batteries. The rechargeable batteries can be recharged because they used a reaction that's a lot easier to reverse. So what types of reactions are easier to reverse? Well, we look at the collisions that are involved in the reactions. And when we look at the collisions that are involved, this involves collision theory of chemical reactions. Collision theory is just part of quantum mechanics. A little subcategory, just looking at the collisions themselves. And so we look at how things collide at the particulate level. That's basically it for this. And so the first bullet point is we're looking at the particulate level collisions. The second bullet point is this, states that sufficient kinetic energy and proper orientation are necessary. Third bullet point, chemical reactions will overall affect a huge number of collisions for an individual collision. Okay, for these bullet points, there's only two things on this slide. One, particles collide. Two, when they collide, they have to collide with enough energy. You know, water molecules can collide, but that doesn't mean they're going to react, you know. If I had 1 billion water molecules, only like 4 out of 1 billion have enough energy to react. Oh, actually, I need to take that back because it's probably more than 4 out of 1 billion.
Momentary dipole and stuff forming?
Yeah, momentary dipoles are formed. The temporary dipoles, which would be dispersion type forces, those are always forming, and those are always breaking. But what we have is momentary, what we call a transition state. So there's a big collision like this, and things are transitioning from breaking bonds and forming bonds. That's what, and in those we would have dipoles as well, momentary or temporary. But getting back to this, the water molecules have to collide in the correct orientation. So if 2 hydrogens come together to collide, that's not going to result in a reaction. What we have to have is an oxygen colliding with a hydrogen. Then we're going to get a reaction. And so we need enough kinetic energy and we need the proper orientation. So there's a lot of verbiage on this slide, but basically collision theory just says this: 2 particles collide, they have to have the right energy and the right orientation. And that's the take-home message of this slide. Let's look at the orientation. This is a successful orientation here. You know, we want to make it red and blue. Looks like this is success too, huh? No, this is unsuccessful. You see? We make products. This was unsuccessful. And so it depends on how the molecules collide. They've got to collide with the right orientation to form a new bond. And so this one is it. When we look at things at the particular level, there are a lot of molecules, you know, in a gram. And so there are a lot of collisions, but out of all those collisions, only a tiny fraction will be successful. And that can result in explosive reactions, even, you know, just having enough, or it could result in very slow reactions. Let's look at the energies in a little bit more detail. This conversion of kinetic to potential, forget about that. Transition state, this is it. When things collide, what happens is bonds have to break and bonds have to form. And so if we try to visualize, you know, how do the bonds break and how do the bonds form, that's what's called the transition state. So the transition state is the state in which, you know, bonds are starting to break and bonds are starting to form. It's just trying to get it's not something that you can isolate because it's like a midway point, you know, in the transition. One's transitioning from reacting to product. And so it's something we don't isolate. Therefore, it's called an unstable state. It's an unstable state because we don't really isolate it. Good transition state. There's a potential energy barrier for the collision. That's why we have to have a certain energy. And that energy is called the activation energy, which is the minimum. And so this one, this potential energy barrier, ignore that. Activation energy, we want to know that. Let's talk about this in just a minute. So here's the anatomy of a successful collision. Let's first look at this plot. This plot is called a reaction progress plot. Transition state complex reaction progress. That's a long title for this plot. And so a lot of people call this the reaction profile. You know, this kind of maps out how the reaction occurs. This would be a favorable reaction because take a look at the reactants are up here, the products are down here. So to get from reactants to products, is this a downhill process? It looks like it should just be straight downhill shot, right? And then, hey, you know, we got a driving force. We got a driving force for this reaction because products are more stable. But it's not a downhill shot. It's not a downhill shot because of this. This is called a potential energy barrier, but we don't need to know that. We just need to know that there's going to be an energy associated with this. We have to have a successful collision. That collision's got to result in bond breakage. Bond breakage costs us energy. When we break bonds, it costs us energy. Boom. But we're also forming new bonds. Forming new bonds releases energy. So in this transition, it's costing us and giving back some energy. Overall, we get all the energy back when the new bonds are formed here. But we got to do some bond breakage here, and so this is this intermediate state. This intermediate state we don't actually capture. You can't capture this. You know, this is like this is moving from here to here. The only thing we can capture are the reactants we can get and the products we can get. So typically we just think in terms of reactants and products. But when we're looking at collision theory, then we try to visualize what's happening in going from reactant to product. And going from reactant to product, it's not downhill, even though products are more stable. We got to first climb up the hill, and then we can go downhill. We can see this in a lot of reactions here. Like, for example, methane and oxygen should react. There's a big driving force for that, right? But if I release methane into this room, do you see the flame? You don't see the flame. Why not? We don't see the flame because there's this uphill. You know, the methane and the oxygen have to collide with enough energy to get going. Well, they are. They're colliding with enough energy, but how many methane molecules and oxygen molecules have enough energy to climb this hill? Not that many. The reaction is occurring right now, but you can't see it because it's so slow. We need it to help it. You know how we can help this reaction go?
You heat it up.
You heat it up. If I had a hot surface, you don't need a flame. You just need a hot surface. Why? If you heat it up, that is, if I had a hot object, like a hot piece of metal, with no spark around, no flame around, it'll ignite. You know? Why is that? Yeah, because we excite the atom. So we just need to give it a little kick. We give it a little kick, it goes up here. But don't I have to continually excite the atoms? Don't I continually have to heat it up? No. I don't have to continually heat it up because once I get enough molecules to go over the hill, then when they go down the hill, they release enough energy to heat up the molecules behind it. And so it's only the pioneers, only the first molecules I got to kick over the hill. And the rest are going to benefit from the energy that's released in forming the new bonds. Does that make sense? Okay. So yeah, this is a very favorable reaction. Look at it. This is happening. There's a very favorable reaction here, but it has this energy barrier. The energy barrier we call the activation energy. So that could slow down. Yeah. Activation energy. The reverse reaction, this one's heavily favored. This one would be harder to reverse because to reverse this reaction, you know, it's going to cost you a lot more energy. These bonds are more stable, so it's going to cost you a lot more energy to go over that hump. So this is a reaction that may not be as easy to reverse, but potentially 280s to 1. This is just talking about kinetic versus potential energy. We talked about the swing, right? This is back in chapter 1. Here, you know, kinetic energy is the energy of motion. So here at the bottom of the swing is where we have max kinetic energy. And then at the top of the swing, that kinetic energy is transformed into what we call potential energy until they stop. When they stop here, what's the kinetic energy? Zero. And so this is the same thing. you need a violent collision because the violent collision is going to break the bonds. Well, that violent collision is going to turn the kinetic energy into potential energy to break the bonds. So this is just showing this, this activation hump. That's the activation area. Yeah. That's what this slide is. This slide, I just skipped it. It's not that important. You learn a lot about kinetic and potential energy in physics in Chem 1B. But, here, conditions that affect the rate of the reaction. Obviously, temperature. What's temperature going to do? Well, temperature is going to increase the population of higher energy molecules. Do you guys remember the curve? What happens with temperature? So room temperature, very few molecules have enough energy to climb the hill. This is methane and oxygen. Very few molecules have enough energy, but if I just heat it up, then I'll get a lot more. That's because when I look at the kinetic energy, or this is the kinetic. Kinetic energy is what again? Energy of motion. When I look at the population distribution of population, we get the energy distribution, the kinetic energy distribution. A room temperature might look like this, or if I go at higher temperatures, what's going to happen is the lower energy population is going to decrease, and the higher energy population is going to increase. So this is a temperature greater than room temperature, so T is greater than RT. If I cool it down, then I'm going to increase the lower energy population and decrease the higher energy population. So this is at temperatures less than RT. So obviously this is going to have a huge impact on how many molecules have sufficient energy to hit the EA. This energy cutoff is the activation energy, EA. And so if the bonds are really strong, the EA increases. If the bonds are really weak, the EA decreases. Depending on it. And so the EA shifts depending on the reaction itself, but the population is also going to shift depending on the temperature. And so at higher temperature, regardless of what your EA is, you're going to have a greater population of molecules that can climb over the hill and react. And therefore, if there's a greater population, you're going to get more collisions. More collisions will result in more reaction. And that's what we call the rate of reaction, the rate of reaction. In fact, you got to be careful because some of these reactions can be quite explosive if you get too fast. So reactions are faster at higher temperature and slower at lower temperature. Yeah, the population is based on population. Right? EA, the activation energy, is the same. Yeah, the EA is the same. It's fixed because of the bond. It's just the population. EA is the minimum kinetic energy that the particle must have to enter a reaction-producing collision. And so for water, that's pretty high up there. But for other reactions, it's kind of low. Okay, does that make sense? This? You get a move. So what do we see here? See the same thing. Do you see? This curve is very important. This is at a given temperature. So at a given temperature, at 25 degrees C is this blue line, room temperature. Here's the population. This is EA. In this case, it's 262. 62 kilojoules per mole. So what we're looking at is 25 degrees C is the average kinetic energy, but if you look at the kinetic energy for individual molecules, it's all over the place. It's just the average kinetic energy, which is somewhere around here, is here. At 75 degrees C, the average kinetic energy is higher, which means the population just shifted to the right. Boltzmann distribution, energy distribution. Conditions that affect the rate of the reaction. Temperature affects the rate of reaction. What does temperature do to the rate of reaction?
Increasing temperature.
Yeah, increasing temperature will increase the
rate.
rate. Yeah, increasing temperature increases the number of collisions. Yeah. Increases the average kinetic energy, increases the population. So temperature is the biggest. We use temperature. Likewise, if we don't want reactions to go fast, we want reactions to go slow, what would we do? We'd cool them down. So when I was doing potentially explosive reactions, I always made sure to try to cool them down, so they would react less violently. Some reactions you just want to happen fast at room temperature. You don't want to heat them up, or some, even if you heat them up, they're still kind of slow. So people are looking at changing the activation energy. How can we change the activation energy? Well, how can you? I mean, you've got bonds to break and bonds to form. Well, it turns out that a catalyst is good. Catalysts are good because catalysts, the way they work is they lower the activation energy. And so at a given temperature, if you lower the activation energy, you're going to increase the population. And so, in other words, you lower the hill. So if you're going, this is called the reaction profile. You got to climb this hill. If we can lower the hill, then a lot more molecules can get over that hill. The activation energy. This hill is called the activation energy. E sub A. So, red is the normal hill that has to be climbed, but if you introduce a catalyst, you make the hill smaller. Well, how do you make the hill smaller? Well, this is showing the same thing. If we introduce a catalyst, we make the hill smaller, that is lower energy, thereby increasing the population. So how do we make the hill smaller?
Catalyst.
With a catalyst, how do catalysts make this hill smaller? How do catalysts work? This doesn't say how catalysts work, so let's just briefly take a look at catalysts here. Going to Wikipedia. Here's a catalyst. This is called a heterogeneous catalyst, or also a homogeneous catalyst. And basically, what a catalyst does is it changes the collisions that need to take place, or they help weaken the bond. And so let's see if we have a cartoon. Here's the hill without catalyst in black. Here's the hills, but you can see there are a lot of little hills now. That's because in this particular case, they changed how the reaction takes place. We still get the same reaction, but it's kind of a different way that it takes place. So let's look for enzyme catalyst. Enzymes are catalysts. different ways we can look at catalysts here. Here's one where we have this intramolecular reaction. Intra is within the molecule, so there's some stuff happening here inside the molecule. But if we add a catalyst, then we end up getting the same product, but the way the reaction occurs is different. This is called acid catalyzed reaction. And so in this acid catalyzed reaction, it changes the way we can rearrange the electron. Change that, then it lowers the energy barrier for this reaction to occur. We end up getting the same product, and it spits out the original catalyst that we had used in the first step here. We regenerate the catalyst, so it's not consumed as a reactant. It's regenerated. That's one way. There's other catalysts that do this. And this is just a cartoon showing it here. But a catalyst either facilitate breaking bonds or forming bonds. So in this case, the catalysts bring the two molecules together so that they can form the bond more easily. In other cases, it would be the reverse. The catalyst helps break the bond. They're intermolecular attractions. Intermolecular attractions would be temporary dipole, London dispersion, permanent dipole, or hydrogen bonding. These interactions, these intermolecular attractions, puts tensile force on the bond. Tensile is pulling, and so it pulls apart on the bond, making the bond easier to break. And so catalysts can help facilitate in breaking bonds. The reverse here, by pulling them apart, or they can facilitate in making bonds by bringing the molecules together. And so that's how they're going to lower the activation for the bond. Other conditions that affect the rate, concentration. Higher concentrations, we can get more collisions. So things at higher concentrations tend to react faster. Well, that's talking about the rate. It's called kinetics. Now we're going to move on. This is showing the achievement of the state of dynamic equilibrium. Here we have the rate of the forward reaction, here we have the rate of the reverse reaction. The forward reaction rate increases, we'll start making more product. As we make more product, the product molecules can collide, cause a reverse. Eventually we'll hit a state of dynamic equilibrium in which the rate of the forward reaction equals the rate of the reverse reaction. No further change occurs. So it's shown on this curve, but it's not important. No. The organization of this is kind of funny. But, we'll just go with the organization because I'm taking the book. Le Chatelier's principle. Once we hit the state of dynamic equilibrium, then the rate of forward and rate of reverse are equal. Like in this case, water molecules can move to the right, water molecules can move to the left. And they're going to be moving at the same rate. It doesn't matter if those two sides are balanced or not. So, concentration effect. Okay. So let's look at the Chatelier's like this. Look at Le Chatelier's principle. We could have this, this reactant, this product. In this case, which side's favored? The reactant or the product?
Reactant.
Reactant side's favored. Are more molecules moving left to right, or right to left, or is it the same in both directions? It's the same in both directions, otherwise the two water levels wouldn't be equal. And so the rate of the forward reaction equals the rate of the reverse reaction. And we've reached the state of dynamic equilibrium. Before this, I could have poured, all the water on the reactant side. If I put all 50 gallons here and there's no water here, what's going to happen? Well, the rate of the forward is going to exceed the rate of the reverse. And then what's going to happen is, as I get more and more water here, then the reverse is going to start increasing. And eventually, the reverse is going to match the forward, and we've reached the state of equilibrium. That's all that's saying in that earlier chart. And so here we've done this. Now, what's going to happen is if I do this, and so this is called the concentration effect. Things that screw up. And so if I increase the reactant concentration, the square brackets means the molar concentration. In other words, if I put more reactant in, which way will the water go? If I pour more water into the left side, the water obviously is going to go to the right side. And so we call that the shift. And so the reaction goes to the right. Reaction goes right. I don't care how fast or how slow this is. What we're looking at earlier was how fast or how slow this is. Now we don't care about how fast or how slow this is, because this reaction is mixing up two major topics in chemistry that we normally keep separate. The two topics in chemistry are how fast, and the other topic is equilibrium, which side's favored. How fast is called kinetics, and where it lies is called thermodynamics. And this is mixing the two up because they aren't, necessarily. Some things are, sometimes they go hand in hand. So, for example, if the products are heavily favored, it could be an explosive reaction. But other times they aren't. If the products are heavily favored, it's a slow reaction. Doesn't matter how long, because of the mechanism of the reaction. And so right now, we don't care how long this takes or how fast or how slow it is. It just shifts to the right. The reaction goes right. What happens if we decrease the reactant? So if we remove water here, it's going to shift to the left. What happens if we increase the product concentration? Let's say we pour more water in the product, it's going to shift to the left. And if we decrease, it shifts to the right. So if we start removing water here, it's going to shift to the right. This is Le Chatelier's principle. And the same thing goes with pressure. Pressure and concentration are related for gases. So if I'm looking at gases, the pressure of the reactants, if I increase the pressure of the reactants, it shifts to the right. If I decrease the pressure of the reactants, it shifts to the left. Increase the pressure of the product, shift to the left. Decrease the pressure of the product, it shifts to the right. And so pressure and the higher the pressure, the more concentrated the gas must be in that sense, at a given temperature. So that's the concentration effect. I don't want to talk about this in detail, but let's just go straight to the example. Like this slide, skip this slide. Figure 1812. Okay. This is what we care about. Okay, we're going to increase the H2S concentration. Which way is it going to shift? Well, H2S is a reactant or product?
Reactant.
Increase the reactant concentration, it shifts to the right. And so increase H2S, it shifts right. What if we increase the H2? Well, H2 is a product. If we increase the H2, it's going to shift left. If we increase the H2S, it shifts to the right. It's forward. If we increase H2, it shifts to the left. It's reverse. That's it. Yeah, but whoever wrote these slides is very wordy. There's Crocolici, I think, is maybe very verbose. But anyway, the volume effect. Now this is tricky. The volume effect is tricky because the volume is going to impact the concentration, but you think, you know, it impacts the concentration for everything. It does. But it could have a bigger impact on one side versus the other. It depends. And so the volume effect. What happens if you increase the volume? Well, that's tricky because we have to see which side favors bigger volume. So let's skip this. Skip this. And then just take a look at this. Which side favors bigger volume? Well, this is gas, this is gas, this is solid, this is gas. One thing is, which takes up more volume, a mole of gas or a mole of solid? A mole of gas. And so when we look at this, therefore, when we do the volume effect, ignore solids and liquids, because solids and liquids in comparison take up very little volume. So for example, 2 moles of liquid water takes up how much volume? 2 moles of liquid water weighs about how much? A mole of liquid water weighs 18 grams. 2 moles of liquid water would weigh 36 grams. 36 grams is how many milliliters? For water, it's 36 milliliters. So 2 moles of water would be 36 milliliters of liquid water. But do you know how much 2 moles of gaseous water is? 2 moles of gaseous water is 50 liters. 50,000 milliliters. So we're going from 36 milliliters to 50,000 milliliters. The same 36 grams. And therefore, for the volume effect, we only worry about gases. So let's take a look at the volume effect. Let me just summarize all these slides here. So we're just going to say about 25 liters per mole. So this is 25 liters. How many is this? 50 liters. So altogether this is about 75 liters. Over here, what do I have? I have 4 moles of gas. 4 moles of gas, that's how many liters? About 25 liters per mole. That makes 100 liters. So this is 3 moles of gas, 75 liters. This is 4 moles of gas, 100 liters. So which side has more volume? The right side has more volume. Therefore, this is what's going to happen. If I compress the volume, which side is favored? If I compress the volume, make the volume smaller, which side's favored? 75 liter side or the 100 liter side? The 75 liter side. So what's going to happen is the reverse reaction is going to take place to make the volume smaller. So if I compress the volume, the 75 liter side takes up less volume, so it's going to reverse reaction is going to happen, right? So it's going to shift to the left. What happens if I expand the volume? If I expand the volume, then that's going to favor the 100 liter side, and so it's going to shift it to the right. If the volume is reduced, what side does it go? If the volume is reduced, it goes to the 75 liter side, which means a shift to the left, which means reverse reaction. But this is very wordy. So basically all we have to say is the shift is in the reverse, or the shift is to the left. So reduce the volume shifts left, increase the volume shifts right for this reaction. For other reactions, there might not be any shift. So for example, let's say both sides were the same volume. If I have the same volume on the left and the right, then it makes no difference. There's no shift. So if this were 75 liters and 75 liters, it doesn't matter. Nothing's going to change. Here they say molecules change from 4 on the right to 3 on the left. That's the gas, moles of gas. Change in temperature. Volume effect. Okay, increased volume shifts to side with more gas. If both sides have the same number of moles, then no shift. If we decrease the volume, then this shifts to side with less gas. Temperature. The temperature is tricky, but the way we can think of it is this. For exothermic, like this, like water goes to ice. In order for water to go to ice, do you have to add heat or do you have to remove heat? We have to remove heat. How do we remove heat? Well, we have a freezer. The freezer is going to take the heat out. And so this is it. If we add heat, do we make more ice or do we make more water if we add heat? If we add heat, then it's got to shift to the left. The shift is to the left, we're going to make more water. If we remove heat, then the shift is to the right, we make more ice. That's for exothermic. That's for any exothermic. It doesn't have to be water, it could be any exothermic reaction. So we're going to work the same. Exothermic heat is a product. Endothermic. Heat is a reactant. So if we look at endothermic reactions, ice plus heat. Ice plus heat gives water. We're going to melt the ice. And so this is the reactant. And so if we have an endothermic, then we add heat. We add heat, oh, that's good. That's going to shift it to the right. If we remove heat, that's going to shift it the opposite direction. If we remove heat, we're taking away the heat, it's going to shift to the left. So this would be like melting ice. Melting ice is endothermic. Freezing water is exothermic. And so we can predict it. And so this one is easy to predict. Is this an exothermic or is this an endothermic? Is heat a product or heat a reactant? Heat is a product, so we call that exothermic or endothermic? Exothermic. And so here, if we add heat, which way does it shift? To to the left, so we're going to make more NO2. If we remove heat, we're going to shift it to the right. So this is what it's trying to show. We add heat, we're going to make more NO2. When we remove heat, we're going to make more N2O4. Is this endothermic or exothermic? This is endothermic. So temperature is reduced. Temperature is reduced, we're removing heat. If temperature is reduced, which way is it going to shift? So we're removing heat. Removing heat is going to shift this to the left. So the shift is to the left. So after all this, reverse. It's the left. So it's kind of a wordy answer. But all I'm looking for is it shifts left. Remove heat shifts left. Add heat would shift this to the right.
So, Professor, how would you say you're adding heat in that scenario?
We're just adding more kilojoules. If we add heat to this, then we're just adding more kilojoules. It's like adding more reactant, which is going to shift it to the right. If we remove heat, we're just removing kilojoules from here. It's going to shift it backwards. So this is like adding water. If we add water,
So you'd have to add more, like, I'm confused because like right now it looks like you're adding 176 kilojoules to
yeah, per
calcium
mole.
carbonate.
This is the mole ratio. If I add more heat, then I can react more moles of calcium carbonate. 176 is the amount of heat required for 1 mole of calcium carbonate. Let's say I only had 100 kilojoules. If I only had 100 kilojoules, then that's my limiting reagent. I'm going to react less than a mole of calcium carbonate. You know, it's what I'm saying is this. What's a mole of water? Mole of water is 18 grams or 18 milliliters. At 100 degrees C, if I took 44 kilojoules, I could boil 1 mole of water, 18 milliliters of water. But hey, what if I only had 40 kilojoules? If you only have 40 kilojoules, then that's your limiting reagent, and you're going to boil less than 18 milliliters of water. You boil like 14 milliliters of water instead of 18 milliliters of water. Right? What if you had more? Let's say I had 88 kilojoules. If you had 88 kilojoules, then you have enough energy to boil 2 moles of water, 36 milliliters. So adding more or less, this is just telling us the proper ratio. Stoichiometry doesn't mean we have to have that. You know, in limiting reagent problems, that's the correct ratio, the correct stoichiometric ratio. But in limiting reagent problems, often we don't have the correct ratio, and therefore we aren't going to get complete reaction of both components. And so if we had less than 176 kilojoules, we were just not going to get as much. Now what you're thinking about is you might be thinking about quantum. Remember quantum? If the energy were quantized, then we need a minimum energy to step up to the next step. So what in energy quantization, what that means is if you don't have, let's say this is 176 kilojoules. and you don't have 176 kilojoules, then forget it. You aren't going to make it. Because you have to have a minimum, that, in other words, that's a discrete energy. And so what that would be is anything below that would be forbidden. This is why in the hydrogen lamp, you don't see all colors of red light. You only see one color of red light because they had to make that step up. But what happened to all the other shades of red? All the other shades of red were forbidden. Is that kind of what you're getting at, or not really?
No. So when I think of exothermic, you think of releasing heat. Endothermic, you're
Consuming heat.
consuming heat, right?
Yeah. Well,
Okay, wait, hold on. So like for this example, wouldn't you be adding? You wouldn't be adding heat, and it wouldn't be a right shift, or you would be adding heat because you're adding 176 kilojoules.
you need to add heat to get this reaction to go. If there's no heat, this reaction doesn't
So
go.
it's a right shift then.
Yeah. So adding heat will shift this to the right. This is like melting ice. And the more heat you add, the more ice you melt, the more reaction you'll have. So we need to add heat to get this reaction to go. Think about if you have some marble tile or something like that, or statue, a marble statue. Is a marble statue, is that generating CO2 gas being transformed into calcium oxide? No. You have to heat it. This is actually, you have to heat it to a very high temperature to get this reaction to go. This reaction is very important. This reaction, there's a documentary I've watched on this very specific reaction. It's a documentary about, and I think I mentioned this before, about the Romans. You know, the Romans came up with concrete. You know, concrete architecturally has allowed them to make some, you know, magnificent structures. And so they were talking about how they came up, and how they came up with this is they had time to do experiments like this. This actually required quite a lot of heat to get this reaction. And they were lucky, they had time to do this, and they had a source that could generate a lot of heat, and that was coal. From that coal, they could get these high temperatures required for this particular reaction to go. And so it's a confluence of things. Whereas in certain other cultures, they didn't have that. They never generated this type of concrete. That kind of thing. Oh, well, anyway, so your question was, is endothermic versus exothermic?
Because so the reaction's reverse.
Well, that's because we're reducing, so we're removing heat. If we remove the heat, then it's going to favor the shifting it to the
Oh,
left.
okay, that's it. Okay.
So if we take away water here, it's going to shift it this way. If we add water, it shifts it that way. But water is a bad analogy. You'll find out in Chem will be, but it's good for visualizing things. You know, if you have a water tank. So anyway, this is kind of a wordy answer. Basically, we remove heat, it shifts to the left. That's all we need to know. All right. We have something called the equilibrium constant, which we saw earlier. Do you remember what the equilibrium? We saw this before. KW. Water autoionization equilibrium constant. What K is used for doing stoichiometry, partial reaction. And we talk about that. When I say partial reaction, the reaction is done. It just didn't completely react, or it didn't completely go no reaction. There was a little bit of reaction that took place, but it's pretty much done. The stoichiometry of partial reactions, we use K to determine, the amount of reaction that occurs. How much reactant and product. We have at the end. The end of the reaction is that, you give enough time. All K is the ratio. I'll just tell you what K is. K is the ratio of product over reactants, but a little bit more complicated than that. So let's take a look at a generic reaction, A, B, B, where A is the coefficient and little a is the coefficient, and big A is the whatever it is, GG plus HA. So K is just the ratio, but it's a funny ratio because K is going to be the concentration of G raised to little g power, concentration of H raised to little h power. This is equal to a constant for a given reaction at a given temperature. For a given reaction at a given temperature. So it doesn't matter, just the amounts of whatever I put in there, it always has to give me the same ratio at the end. At the end of the reaction, when the reaction's done, it has to give me this ratio. And so if we know what the ratio is supposed to be at the end, then we could figure out, how much reaction occurs if we're given what we have at the beginning. And so what does this slide say? For any equilibrium at a given temperature, the ratio of the product of the concentrations of the species on the right side of the equilibrium equation, each raised to the power equal to its coefficient in the equation to the corresponding product of the concentration on the left side of the equation, each raised to a power equal to its coefficient in the equation is a constant. It's just in words. This shows no matter how I start the reaction, the ratio is going to be the same at the end. And so we can do whatever we want with the reactants and the products, but when it's finished reacting, the reactant and so the stoichiometry is tricky. When I look at the stoichiometry, I'd say 1 mole of hydrogen plus 1 mole of iodine yields 2 moles of HI. And so normally you'd go, okay, if I have a mole of hydrogen and a mole of iodine, they're going to react to form 2 moles of product. And so stoichiometry is easy there, right? The problem is this is a partial reaction. We have to be told that. And so we can't use our standard stoichiometry. We spent a chapter dealing with more than one chapter because we did gas stoichiometry, we did solution stoichiometry, we did standard stoichiometry, mass stoichiometry. So we did already at least 3 chapters of stoichiometry. We can't use those techniques here for this particular one because this is what we call a reversible or equilibrium type scenario. There's not a huge difference in driving gas. There's a huge difference. HI was way more stable. Then we just use our standard stoichiometry. Or if there's a huge difference, there's no reaction. No reaction means we don't have to do any stoichiometry. Nothing reacts, right? In this case, there's some kind of balance between the two. When I look at which side does it look like it's favored slightly? Well, if I look at this number is greater than 1. A number greater than 1 means that the products are more favored because the ratio of products to reactants greater than 1, products are more stable. Numbers less than 1 means that the reactants are more stable. That depends on how much. This number is not huge, 51.5. But anyway, it doesn't matter what I start off with. And so here they put in 1 molar H2 and 1 molar iodine and 0 molar HI. At the end of the reaction, did all of it react? No. If I put in 1 molar, I'm left with 0.218 molar that won't react. No matter how long I wait, it's not going to react. And so what percentage? Well, close to 80% reaction. Well, that's it. It's going to stop there. It's about 80% reaction. Well, if it's 80% reaction here, isn't it 80% reaction always? No, because it's tricky. And so it'd be great if we can just go percent reaction. You know, this one always reacts 80%, but it doesn't. It's funny, but it doesn't. The percent reaction changes depending on the conditions. You know, the initial conditions here. But anyway, what we have here is this ratio. When we do the ratio of HI, now we have to square it. Why? Because it has a 2 as a coefficient. But why do we have to square it? Where does the equation come from? Well, this is part of what we call the scientific method. What was the scientific method again? Scientific method was you take your observations and then you look for patterns. Well, it turns out if we didn't square it, then there's no pattern. If we square it, there's a pattern. And so this is the only way it works. Somebody figured out the pattern. That's it. And so this is what we call an empirical equation. This equation is the equation that fits the pattern. Now, is that good? Well, yeah, it's good because we can use the pattern to now make any kind of prediction. But it's bad. Where did the pattern come from? Well, that's what we need theory for. Okay, so this is what we call a law. What's the reason or the interpretation of this law? We aren't going to get into it. We just, all we're going to do is, well, if the pattern works, let's use it for stoichiometry, that's all. And take a look at all these. It doesn't matter what we come up with. This is a reversible reaction. So if we start off with all products, that means we put all the water on the right side, then some of the water is going to move over to the left side. And so this is exactly what happened. We put all the atoms on the right side, some of the atoms are going to move to the left. And so what we end up with is same number. Now that is like 80% reaction, but if we did 1 molar rather than 2 molar, then we don't get 80% reaction. We get less. If we do 1 and 0.5, we don't get 80% reaction. So the percent reaction changes depending on our initial concentrations, but the ratio always stays the same. This is why, how hard was it? When you look at these numbers, do you see that pattern here? I mean, if you didn't know this pattern, do you see a pattern to these numbers? Look at these 3 columns here. Look at these numbers, and can you tell just by looking at it what the pattern is? I can't. I look at these set of numbers, and what's connecting all 4 sets of numbers? Well, it turns out this is a pattern. I wouldn't have guessed this, but somebody figured it out. And so that's why finding out patterns is sometimes it's hard, because you look at this, you know, what's the pattern here? You might go 80%, okay, that pattern holds here, but it fails here. Do you see what I mean? Sometimes the patterns aren't so easy to see. And so people try to do things with mathematical equations and whatnot. But we don't have to do this because somebody already figured out the pattern. If somebody already figured out the pattern, then all we need to do is use that pattern. This is the pattern here. Except I didn't use CD, I used GH. I used GH because there could be more than 3 reactions. I don't think there are more than 6, so that's why I used the more than 4. C, D, E, F, G. More than 5. But it doesn't matter, it's the products over the reactants, it's the ratio. This is just reaching the state of equilibrium. We're going to hit that pattern. Once we reach that correct ratio, then the reaction is done. If we don't have the correct ratio to begin with, then there's going to be a reaction. So we need that correct ratio. This is the correct ratio here. So write the equilibrium constant expression for the equilibrium here. What they mean by the equilibrium constant is this is just a ratio. K is equal to the ratio of the products over the reactants. So this will be K is equal to the NH3 concentration squared divided by the N2 concentration divided by the H2 concentration raised to what power? The third. So the NH3 concentration squared divided by the N2 divided by the H2 cubed. That's it. What's the number? Well, somebody's got to figure out the number. They didn't give us the number. So somebody's got to figure out what the number is. Well, the somebody just measures it. You know, after this reaction is done, what is the number? And then they plug it in here and then they get the ratio. Lots of people have done it. There are other ways. Once we know the theory, there are other ways we could get this without doing any experimentation. Here's the number here. Take a look at this ratio. Is this ratio a big number or a small number? Very big, which means mostly product. Very little reactant.
Okay.
So, how big do these numbers get? This is very big. It's huge. This is almost like, this we do regular stoichiometry on, Chem 1A stoichiometry. If the equilibrium constant is very large, greater than 1, then the forward reaction is favored. It's a hard cutoff here. You know, the closer we get to 1, K is equal to 1, the more balanced it is between reactant and product. And so they're giving you a cutoff here. If K is greater than 1, it's pretty much products. If K is less than 0.01, it's a 100 to 1 ratio. A 100 to 1 ratio in Chem 1B we use a little different. We use more like 10 billion to 1. If it's a 10 billion to 1 ratio, then we don't bother doing this type of equilibrium stuff. We just do Chem 1A stoichiometry, Chem 4 type stoichiometry. Or 1 to a billion. If it's 1 to a billion, then don't bother. This slide is not very valuable, I think, because it doesn't really give us. So how do we do the stoichiometry? Well, the way we do stoichiometry is we do what's called an ICE. And then we get equations that we solve. That's how we do it. What is ICE? Well, it depends on what we're dealing with. So, you know, I'm following in the order of the book, but the organization is a little bit funny because here they tell us about the equilibrium concentrations, the calculations, but they don't give us an example. And then they go on to different types of Ks. So we have K of the reaction, and then we have different types of reactions. And that's going to lead to different Ks. So for example, we have KW. You remember KW? And then we have something called KSP. And then we have something called KA. KSP is for dissolving solids. Ka is for acids. And then we have something called KB. KB is for bases. So this is acids hydrolysis. It's Ka. Kb is for base hydrolysis. So this is solid dissolving. This is silver chloride dissolving. And so the K is, we call this KSP. KSP stands for solubility product. And it's going to be the ratio of the products of the reactants. So we take silver, which is to the first, and chloride to the first. However, what about silver chloride? Silver chloride is this. In all Ks, for all K expressions, pure solids and liquids, the concentration is constant. Omit from K expression. So let's say you had a half gallon of milk. If you drink, let's say half of it, so I have a half gallon milk, I drink half of it, will it be half as concentrated now? Or is it the same concentration? The same concentration, you just have half of what you originally had. Did the concentration change? No, the same thing happens. If I start off with pure silver chloride, 10 grams of pure silver chloride, I start off with 10 grams of pure silver chloride and let's say 500 milligrams dissolved. Does that mean the rest of my silver chloride is no longer? In other words, this, is it still pure silver chloride? Let's say I had 10 grams of gold and you gave me 1 gram. They're always welcome to do. If you have 10 grams of gold, you gave me 1 gram of gold, is your gold still, your gold's no longer pure because now you only have 9 grams of gold and you gave me 1 gram. Is your gold no longer pure? Or is it still pure gold? It's still pure gold, you just have 9 grams of it. Well, the same thing. If you start off with 100% pure silver chloride and you gave some of the silver chloride to water, is the remaining silver chloride that you have less concentrated? No, it's the same it's pure. So the concentrations don't change. And therefore, if I look at this, this should be divided by the concentration of silver chloride. It's not. Because silver chloride is a pure solid. So this is just for demonstration purposes. This is not going to be on the test. So I have a silver chloride solid, and some of it's going to dissolve to form aqueous silver ions and aqueous chloride ions. So this is called dissolution or dissolving. And I know how much is going to dissolve. I mean, I know how much reaction is going to take place because I know what the ratio is at the end. The ratio at the end is 1.3 times 10 to the minus 5. 10 to the minus 5 is like 1 to 10,000, 1 part to 10,000 parts, which means that which side's favored? Reactant side or product side? Reactants are favored. By a lot. But we still can figure out what's going to happen here because this is the ratio of the products. So what are the products? Silver ion raised to the first. Well, I'm not going to write 1 here. And chloride ions raised to the first. Divided by the silver chloride. But silver chloride is a pure solid, and therefore its concentration doesn't change. Therefore, we omit this. Omit pure solids and liquids. And so it just ends up that this comes out to silver ion and chloride ion. So at the end of this reaction, we have to have the silver ions and the chloride ions make this ratio. So how do we do this? Well, we set up what's called an ice table. This is our ice table here. Now, in the ice table, pure solids are omitted. We omit the ice table. And so we can see how much reaction is going to take place. If we have silver chloride, we assume that none of it has dissolved initially. So none of it's dissolved. Is that where we're going to end up? No, because if we plug that in here, 0 times 0 is 0, which is not this. It's not that. So how much dissolve? Well, something's got to dissolve. Something's got to dissolve to give us the correct ratio. And so how much dissolves is this? I don't know. I'm just going to call it plus x. And so ice means initial. C means change. There's got to be some kind of change because the initial's not right. And so the change is going to be plus x molar. For every silver, I got to form a chloride. And so at the end, this is at the end or equilibrium. I need the right ratio. Well, what is the right ratio? I don't know. It's going to be 0 plus x, which gives me x molar, and 0 plus x, which gives me x molar. And so this is the system of equations I have. X is the concentration of silver ion, which happens to be the same as the concentration of chloride ion, so 1 to 1 mole ratio. And so this has to be this. And so this is going to give me x times x, which is going to give me x squared. And therefore x is the square root of 1.3 times 10 to the minus 5. X is equal to the square root of 1.3 times 10 to the minus 5, and then I'll add the units because K doesn't have units, so I got to add the units here. Molar. And so what is the square root of 1.3 times 10 to the minus 5? .0036. 0.00360 molar. And so that means, well, I'm going to start off with 0, and then at the end of this, I'm going to get 0.00360 molar and 0.00360 molar. And so I just did the stoichiometry. For every liter I'm gonna get 0.0036 moles of silver chloride that dissolves. That's how I do it. Oops. That's not what they were doing here. I screwed this one up, sorry. I thought they gave us the K. They gave us the chloride concentration, 1.3. I'll say if KSP equals that, that's what we do. Are we out?
Yeah.
All right. Oh, I'll continue this next time.
So is this stuff gonna be on the test on Thursday?
No.
Or not any of the stuff that we're talking about today is gonna be on the test?
Yeah. Nothing. None of this will be on the test on Thursday. Can I give it to you later? Tomorrow? Or do you need it right now?
Yeah, I get it right now.
Yeah. Be more ready tomorrow.
Do you know if before the semester ends, the grades will be posted?